Hello, everyone. This is our fourth lesson in geometry. We covered some of the essentials, and we also covered parallel and perpendicular lines. Now we're going to talk about triangles and congruence. So triangle basics. If you remember our first lesson, we did an intro to polygons, and one polygon we looked into was the triangle, which had three sides. We didn't really look into it much. We just stated the names of each type of polygon. We noticed that triangle was three sides. So that's exactly the definition of a triangle, a polygon with three sides. There are different ways to classify a triangle, and one of them is by sides. Scalene means there's no congruent sides. So for example, this is scalene. This is pretty exaggerated. But see, let's say this was 2, this was 5, and this was 6. None of the sides are congruent or equal in length. Remember, congruent segments are equal in length. Isosceles means two congruent sides. So something like this. This side's congruent to this. So for example, 5, 5, and 2. Equilateral, three congruent sides. All of them are equal in length to each other. So 2, 2, 2. Notice there's nothing that says one congruent sides because one side can't be congruent. It's impossible to have just one congruent side. You can also classify it by angles. So acute means three acute angles. So acute angle is basically less than 90 degrees, as we talked about earlier. So for example, this can be 60, this can be 59, and this can be 61. Equilateral triangles are also acute. Right means one right angle and two acute angles. So you've probably heard this term before, right triangle. This is the notation for a right angle. So one right angle and these two are acute angles. So for example, 30, 60. This is an important right triangle that we'll talk about later. Obtuse, one obtuse angle and two acute angles. So something like this. This is, I don't know, 120 degrees. This is 30 degrees and this is 30 degrees. Notice, as we'll talk about later, we can prove that this is an isosceles triangle. So it's possible to have an isosceles triangle that's obtuse. Equiangular seems like it's equilateral, but actually it's three congruent angles, not three congruent sides. So since we'll talk about a theorem soon that shows us that the only possible equiangular triangle has 60, 60, and 60 degrees. You might be able to guess what the theorem is now, but we'll go in depth in it soon. Interior angles of a triangle are the original angles inside of the triangle. So let me just draw this triangle. These are the interior angles. They're the original angles inside the triangle. Exterior angles is formed by extending some of the sides. So let me use a different color for this. If we extend these sides, wait, let me extend it this way too. This is an exterior angle. 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 And this is an exterior angle. Notice that, for example, this is not an exterior angle. And do you know why? Because this is a straight line, so it's just 180 degrees. It's the same for all triangles. It's not an exterior angle. The triangle sum theorem, this is what I'm talking about. The interior angles add up to 180 degrees. And this proves that if there are three congruent angles, that means each of them have to be 60 degrees. We can use algebra to prove it. 3x is equal to 180 degrees since they're all the same. X is equal to 60 degrees. Acute angles in a right triangle are complementary. So this is a corollary to the triangle sum theorem, because if we're given this triangle and this is x, we can use algebra. So this is y, for example. X plus y plus 90 is equal to 180. So x plus y is equal to 90. And that's what we're trying to prove. They're complementary. Exterior angle theorem. The measure of exterior angles is equal to the sum of non-adjacent interior angles. So let's say we're talking about this one right here. Oops. Let me color this in. We're talking about this exterior angle. This is an adjacent angle, so we ignore that. These two are not touching it, so they're non-adjacent. So the measure of this, x, is equal to the sum of y and z. X is equal to y plus z. And we can prove this. We know this would have to be 180 minus x. Oops. 180 minus x. So if we add all these together, 180 minus x plus y plus z is equal to 180. We see that y plus z minus x is equal to 0. So y plus z is equal to x, and that's what we were trying to prove. So that's the basics of triangles. Now we're going to talk about congruence and how that relates to triangles. A congruent figure is where all parts of one figure are congruent to the corresponding parts of another figure. As we'll see in triangles, this can mean that this side is congruent to the corresponding side. This is the corresponding side. This is congruent to this, and this is congruent to this. And it also means this angle is congruent to this angle, and so on and so forth for all angles. A congruent statement shows congruence, and important thing, it uses the corresponding vertices. So for example, if we're given this, A, B, and C, and this is D, E, and F, just assume they're congruent right now. Congruent statements shows that ABC, triangle ABC, congruent. Remember we learned this earlier, this is the symbol for congruent, is congruent to triangle DEF. And this is not the same as triangle ABC is congruent to triangle EDF. Because now AB is congruent to DE. But in this case, AB is not congruent to ED. Scratch that. AB is congruent to ED, but AC is not congruent to EF. So in the previous one, AC was congruent to DF, which is what it shows here. AC is congruent to DF. But in this one, it says AC is congruent to EF. So this is congruent to that. Well, that's not actually true in this case. So it's important to write the corresponding vertices. The third angle theorem is if two angles are congruent to the corresponding angles in another triangle, then the third angles are also congruent. Back to our triangles. If this is congruent to this, and this is congruent to this, then this is congruent to this. We can prove this using the triangle sum theorem. Properties of congruent triangles. So now we're actually talking about what to do with congruent triangles. So reflexive ABC is congruent to ABC. Symmetric, if ABC is congruent to DEF, then DEF is congruent to ABC. And transitive, if ABC is congruent to DEF and DEF is congruent to XYZ, then ABC is congruent to XYZ. These look remarkably similar to some properties we learned earlier. A is equal to A. If A is equal to B, then B is equal to A. If A is equal to B and B is equal to C, then A is equal to C. So now we're going to actually prove triangles congruence. We learned what to do with them, now how to prove them. So SSS. Now notice in this slide, I'm going to use abbreviations because that's easier to write down. But S stands for side, A stands for angle, H stands for hypotenuse, and L stands for leg. I'll explain the H and L later, but for now, we're dealing with S for side, A for angle. So SSS means all three sides are congruent, side, side, side. And let me show you an example. I'll only show you an example for this first theorem because it's pretty repetitive. So if we're given this, and we know these two are congruent, these two are congruent, and these two are congruent, that means the two triangles are congruent, and we can show this by transformations. Since we haven't learned transformations yet, I won't prove it, but it's basically saying that we can map this onto here. We can sort of place this triangle onto this triangle to show they're congruent. SAS, so side, angle, side, the two sides and the included angle. So let me just show you a diagram to show you where it is. So side, angle, and side, side, angle, side. And we can do this on the other triangle and show they're congruent, similarly proving by transformations. HL, like I said, H is for hypotenuse, L is for leg. Brief review of right triangles. If you haven't seen one before, this is called the hypotenuse of a right triangle. This is a leg, and this is the other leg. So hypotenuse is always the longest side. So yeah, right triangle only. So the hypotenuse and leg are congruent. If we're given this is congruent and this is congruent to the corresponding triangle, then we know that the entire triangles are congruent. This actually brings up a good question, because can't this work with other triangles too? Well, we need at least 3 points. So how does HL work? We need 3 parts. So the reason is because we know all right angles are congruent. We learned about this in our parallel and perpendicular lesson. All right angles are congruent. So we already know that this angle. So it's side, side, angle. But side, side, the angle doesn't work for normal triangles because there are 2 possible triangles. The point of congruency is that there's exactly one triangle that matches up with the other triangle. So let me actually show you. It's better to see on this. So we're given one side. Oops. We're given one side. We're given another side. Let's just say it's like this. We're not given the angle between them. So instead, we'll say that we're given this side right here, side, but we're not given the angle between them. So what do? Well, first we'll construct this angle, which we're given. And we don't know how long this line runs because we're not given SAS, we're given SSA. So we have another side. But since we don't know the angle over here, it can be anywhere. Notice that if this was the side, then this is a possibility, right? Because this looks like a triangle. But if you use a compass and you actually show, actually I can draw a circle, right? So something like this. Let's assume this is the center. If you draw using a compass, you notice that this, since the circle is the set of points a certain distance, we know the certain distance, we know the center, which is this. So we just need to see where the circle intersects this line and we see the triangle. So this was one possibility, but there's also this possibility. So let me draw that in a different color. There's this, and there's this. Rough drawing. But you see, these are 2 different triangles. They're not congruent, as we can see from this picture. So we can't use SSA. It produces 2 different triangles. ASA, 2 angles in the included side. So look something like this. angle, we're given this. Oops. We're given this angle, we're given this angle and the included side. And AAF, two angles in the non-included side. So we're given this, and the non-included side. This is not included, basically means it's between them. So this is non-included, it's not between them. Or we can also have this side that's congruent, but it basically is the same thing. So another theorem, CP-CTC. And this is not to prove that they're congruent. This is another thing, what to do after they're congruent. Corresponding parts of congruent triangles are congruent. C, P, C, T, C. It's extremely important you remember everything that's on this slide, because all these theorems to prove it, prove triangles congruent, and this is extremely important on what to do after you prove it. So for example, if we're given these two triangles that are congruent, let's just say we knew side, side, side. Then what can we do with it? Well, because of this, we know that this angle is congruent to this angle, and this angle is congruent to this one. And this angle is congruent to this angle. This is a rough drawing, but if I had more time, I could show you an example. I'll probably show you an example at the end of this. So, right, congruent triangles, another application, they can be used to justify constructions. For example, copy an angle. You can use congruent triangles to show that the angles are congruent. We just have to prove that the triangles are congruent, and then we can use CP-CTC. So this actually can be our example of using CP-CTC. So to copy an angle, you have to use the compass and a straight edge to construct this perfect copy. But how can we prove that these are perfect copies? Well, if this is a triangle right here, and this is one too, we don't know these are congruent, but we know this is congruent to this because we said so. We constructed this line. We constructed these triangles such that these are congruent, and same with this, and same with this. So side, side, side. And because of that, these two angles are congruent, which means the angle is a perfect copy. So some special triangles that are important. Isosceles triangles. We talked about this before, but it just says that there's two congruent sides. Some basic parts, legs are congruent sides and the base is the non-congruent side. So let me quickly draw it. If this is congruent to this, then leg, leg, and base. The vertex angle is formed by the legs. So this is the vertex. And the base angle is formed by the base in one of the legs. So this is a base angle. Actually, let me add this here to show that it's an angle. And this is a base angle. So the base angles theorem of isosceles triangles, the base angles of an isosceles triangle are always congruent. Saying that this is congruent to this. And I talked about this briefly. Remember when I told you about that 120, 30, 30? Well, I said soon we'll be able to prove that this is isosceles. Now we can, because we know that these two base angles are congruent, which means triangle is isosceles, is the converse of this theorem. Also notice that the theorems that I introduced in this lessons, unlike the previous lessons, I didn't use if-then format. I just used it in the previous lessons so that you would be comfortable with the if-then format. If you want practice, you can write these theorems in if-then format. This one, for example, would be if a triangle is isosceles, then its base angles are congruent. So another, well, a corollary to this theorem is a triangle is equilateral if and only if it is equiangular. So equilateral, 3 sides congruent, equiangular, 3 angles congruent. So we know, let's try to prove this. We know all equilateral triangles are isosceles because, I mean, it has at least 2 sides congruent. And since they're isosceles, that means this angle is congruent to this angle. But we can also look at it this way. This side is congruent to this side, which means this angle is congruent to this angle, which means all 3 angles are congruent by the transitive property of congruence. This is congruent to this, and this is congruent to this, so this is congruent to this. A congruent to B congruent to C, A congruent to C. So because of this, all 3 sides are congruent, all 3 angles are congruent. Proof. So coordinate proof. It's a nice way to prove. It involves placing geometric figures on the coordinate plane. And we can use things like parallel and perpendicular lines, the distance formula, to actually prove some things are true. It's best if the origin is the vertex and the axis is the side, and / or the figure is in quadrant 1. So I'll actually give you an example of coordinate proof. Let's see if we can prove that let's say given a right triangle, we want to prove, let's say we want to prove the distance formula. So we can actually prove that using a right triangle. So let's say we're given these 2 points. This is not exactly coordinate proof because it's not proving a theorem. It's just proving the distance formula. And this doesn't really have the origin as the vertex and axis as a side and the figure in Q1 because the distance formula is applied to any 2 points. So let's say we're given these 2 points, worst case scenario, and we want to find the distance between them. We can create a right triangle. And if this is x1 comma y1 and this is x2 comma y2, well, if we bring this straight down and bring this straight to the right, that means that this would be, since this line has the same x coordinate as x1, it'll be x1 and x2, and the distance between them is the shortest line, which is horizontal, and we can calculate this to be absolute value of x2 minus x1. It's distance, so it has to be positive, which is why there's the absolute value. This one's similar, since it's directly to the right, we know this has the same y coordinate as y2. So it'll be absolute value of y2 minus y1. Again, we use the absolute value because distance is positive. And now we can use the Pythagorean theorem. Most people should know this, but if not, it's basically saying that in a right triangle, a squared plus b squared is equal to c squared. A, b, c. Done. So here we're given this squared plus this squared is equal to d squared. And we can take the square root of both sides, and we get x2 minus x1 squared plus y2 minus y1 squared. And that is the distance formula in all its glory. Some more things to do with triangles, mid-segments, perpendicular bisectors, altitudes. Soon we'll be talking about angle bisectors and medians. These might seem foreign to you, but now we're going to be talking about special segments in triangles. We're done with congruency, but we might need congruency to prove some of these. A mid-segment, first thing, connects 2 midpoints of a triangle. So if we're given this triangle, and this is a midpoint, this is a midpoint, this, actually I'll use a different color. This is the mid-segment. And there are 3 in each because there are 3 midpoints. And if you know combinatorics, you have to choose 2 points out of 3. So you can either choose this one, or this one. So there's 3 possibilities. These are the different mid-segments in the triangle. Mid-segment theorem, the mid-segment is parallel to and half the length of the third side. So if this third side was, say, C, then this would be 1/2 C, or C over 2. That's an easier way of writing it. And this is parallel to that. Now, notice these three segments, they actually form a triangle. And this triangle is congruent to the original triangle. And you can prove that using similarity, which we haven't done yet, but you can also use it, prove it using coordinate proof. And that's not the only triangle that's formed. There's this one, there's this one, there's this one, and there's this one. There are 4 triangles, and they're congruent to each other. Each of them have 1/4 the area of the total original triangle and 1/2 the perimeter of the original triangle. That's extremely important when it comes to mid-segment problems. And I'll also prove this right here. So let's say we're given this. This is 0, 0, A, 0, and this is B, C. Mid-segment. So the midpoint of this would be B over 2, C over 2. And that's this point right here, point A. I'll call this point X, point Y, and point Z. So then point B would be the midpoint of this. Since we only have to find one midpoint, actually, it'd be easier to do this. We only have to find one mid-segment because once we find one, we can just tilt the triangle and we can find the other one and then tilt it again to find the third one and prove it. So these are the 2 midpoints. And the line connecting these, we can find the equation of the line that connects these and prove that it's parallel to the equation of the line that goes through this side. That would be a lot of work because of all the fractions, but you can do it at home as an exercise if you want to. You can also use the distance formula to prove that this is the distance between these two is 1/2 the distance between these two. So let me just erase these. Concurrency. So a concurrent lines mean that 3 or more figures intersect at one point. In this case, we'll be talking about lines. So these 3 are concurrent because they intersect at this line. This will be important as we talk about the other important segments in a triangle. So perpendicular bisectors of a triangle, they're concurrent. So first of all, a perpendicular bisector is this right here. Bisector, remember we talked about a bisector as being going through the midpoint, and perpendicular is perpendicular to the segment and going through the midpoint. So let's say the midpoint was right here. Then the perpendicular bisector would be here. And then the perpendicular bisector of this would be here. The perpendicular bisector of this would be here. And voila, they do intersect in one point. So they're concurrent. Let me also clear the mid-segment image. So the circumcenter is the point of concurrency. Like I showed you, in this triangle, it was somewhere over here, or it was right here, right? And it's also equidistant from the vertices. That's really important. This is equivalent to this, which is equivalent to this. The circumcircle passes through all the vertices of the figure and it centers the circumcenter. This makes sense because since the circumcenter is equidistant from all the vertices, that means that the length between them is the same. And a circle is the set of all points that are the same distance from a certain center. So if the center was the circumcenter, that means if the center was the circumcenter, that means that the vertices would be on the circle. So it passes through all the vertices of the figure. Altitude, that's another important segment. So an altitude of a triangle is perpendicular from vertex to side. What's the difference between that this and perpendicular bisector? So this was the altitude of the triangle. Actually, let me make it a bit more obvious what the difference is. So this is the altitude. It's from this vertex to this side and it's perpendicular. But the perpendicular bisector, it doesn't have to go through the vertex. This is the perpendicular bisector because it goes through the midpoint and it's perpendicular. This has nothing to do with the vertex. They're also concurrent and they meet at the orthocenter. It's the point of concurrency of altitudes in a triangle. And there's actually nothing special about the orthocenter, but it's useful. Angle bisectors. So we talked about angle bisectors. They bisect the angle. In a triangle, let's say it was this triangle right here. This would be one of the angle bisectors. This would be the other, and this would be the third. And they meet right here. You might not notice anything about this at first. One thing, obviously, they're concurrent because they meet at that point, but this is called the incenter and is the point of concurrency of angle bisectors in a triangle. It's equidistant from the side. So the perpendicular bisectors meet at the circumcenter, which is equidistant from the vertices. This is equidistant from the side. This is equal to this, which is equal to that. In circle, as you can guess, is the circle going through the, whose center is the incenter, and it's tangent to all sides of the figure. So maybe I should use a different color for this. This is the incenter. It's tangent to this, this, and this. And that's because the radius is the distance from the incenter to one of the sides. The medians of the triangle, median is basically a segment that goes through the vertices. So again, it's like this. Oop, different color, I guess. And it goes through the midpoint. So this is one median. The other median is like this. Let's just pretend that goes through the midpoint. And the third one is like this. Similarly, that doesn't really go through the midpoint, but you get the gist of it. The medians are concurrent as we can see. And the centroid, this doesn't end with center, shocker. Okay, so the centroid is the point of concurrency of the medians. And this is a bit more complex than the others, so I'm gonna have to switch colors. This distance from the vertices is twice as long as the distance from the sides. This is the distance from the vertices. And what's a nice color? Yellow. This is the distance from the sides. So A to A. Well, I probably should have switched colors, but still. This is twice as this. And it's the same for the other medians too. It divides the triangle into 6 triangles of equal area. So this, it might not look at it at first, but new color time. This has the same area as this, 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 and this. And another bonus, the centroid is the center of gravity of a triangle. So center of gravity is basically the balance point. If you hold it, using your finger, if you hold up a triangle, let's just say it was made of paper and you cut it out or whatever, and you hold it at that point, it'll balance. If you hold it at another point, it'll fall down. That's why it's so important in things like engineering and physics. So the special segments from the vertex of an isosceles triangle are the same segment. Nice theorem, very useful when we're talking about isosceles triangles. If we're given this isosceles triangle, then This is the altitude. This is the perpendicular bisector. This is the angle bisector. And this is the median. That's amazing because we can use this to solve so many problems, and we can actually prove it rather easily. So let me get rid of the extra junk. Let's just say we only knew that this line is, I know, the median. So if we're given this, we know that this side is congruent to this side, this is congruent to this, and this angle is congruent to this angle. SAS. It's a congruency theorem. So because we know that this we know that this angle is congruent to this angle. And since it forms a linear pair, we learned in last lesson that if two angles form a linear pair and are congruent, they are right angles. So given this, we know that this is the altitude because it forms a right angle and it's from the vertex. We also know that this is the perpendicular bisector because it goes to the midpoint, which is right here, and it's perpendicular. But what about angle bisector? Well, that's also easily proven through CP/CTC. We know that these two triangles are congruent, which means this angle is congruent to this angle. It's an angle bisector. Easy to prove just using congruent triangles. Euler line, or some people pronounce it Euler line. It's a line that passes through the orthocenter, the centroid, and the circumcenter of a triangle. It's too complicated to draw it, but it's pretty useful for physics, engineering, etc. Euler line has a lot of nice properties. You can search it up, get a picture of it, because if I were to draw it, I'd probably be here for the next hour. So some more things about triangles. Inequalities in triangles. You've probably heard one or more of these before, but didn't know it was actually a property. The side angle inequality. You probably guessed this is true, but the angle opposite to a longer side is larger. So if this was a triangle and this side is longer, the angle opposite to it, this, is larger. And this works the other way too. The side opposite to a larger angle is longer, as we can see from here. So we can actually, given the angle measures, we can order the lengths of the sides. Given the side lengths, we can order the measures of the angles. Pretty handy. Triangle inequality is probably the most famous. The sum of any two sides of a triangle is greater than the third side. So given this, A, B, and C, that means A plus B is greater than C. That means B plus C is greater than A, and that means A plus C is greater than B. Or you can all write this in one compact inequality. A minus B is less than C, which is less than A plus B. And this tells you everything you need to know about the lengths of a triangle. Well, not everything, of course, but everything relating to this property. Hinge inequality. So this has to do with two triangles, not just one. So if two sides of a triangle are congruent to the corresponding sides of another triangle, and the included angle of the first triangle is larger, and the third side of the first triangle is longer. So really confusing, but let me just draw it really quickly. So we're given two sides of this triangle is congruent to two sides of this triangle. And the included angle, this one right here, is larger. So this is X, this is Y, and let me actually draw this too. Then the third side, this, of the first triangle is longer. So this basically is just an application of the angle side and side angle inequalities to two triangles. It's basically saying that if this angle is larger than this angle, and these two sides are congruent, that's key, because if they're not congruent, it can vary, the results can be different, because it could have something like this, and this is clearly longer than this, even though this angle is larger than this angle. So given these two properties, that these two sides are congruent and this angle is larger than this angle, that means this side is longer than this side. It's hard to see a problem that involves the hinge inequality, but if you do, now you know. Indirect proof is it's when you assume the conclusion is false and prove the assumption wrong. So if I were to prove that, okay, let me steal something from my first video. If I were to prove that the sky is blue, then I can assume that the conclusion is false. I'll assume that the sky is not blue. And then I can prove the assumption wrong by, I don't know, taking a photo of the sky that shows that the sky is blue, which means that my assumption that the sky is not blue is false. And because that assumption is wrong, that means that the conclusion is not false. That means the conclusion is true. And that's the proof. It's pretty common in geometry. So that's it for today's lesson. Today we talked about congruency and triangles, but next time we'll be talking about similarity and transformations. So similarity, I hinted at this lesson to prove the mid-segment theorem, but next lesson we'll actually get into it. Transformations, I also hinted at to prove the congruence theorems. Both of these are also important. Honestly, everything in geometry is important, so which is why you should watch this series. So see you next week.